You throw a ball. It goes through the left doorway or the right doorway, hits the back wall, leaves a mark. You throw another, same thing. After 1,000 throws, you look at the pattern. What do you see? 2 clusters of marks, one behind each doorway. Makes sense, right? Each ball went through one door or the other. Simple. Now forget tennis balls. Let's do this experiment with electrons. Tiny, tiny particles. The smallest bits of matter we deal with in everyday physics. We shoot electrons at a barrier with 2 slits, very thin slits. And we have a detector behind that clicks every time an electron arrives. Click, click, click. Each click is the same, never half a click. So electrons arrive as whole things, individual lumps, particles. Good. Electrons are particles, just like tennis balls. But now we count where they land. We build up a picture of the pattern. And it's not 2 clusters, it's stripes. A zebra pattern. Lots of electrons here, almost none there. Lots here, none there. Alternating bands. This is what waves do. When 2 waves meet, sometimes they reinforce each other. Bigger wave. Sometimes they cancel each other. Nothing. It's called interference. Like when 2 ripples in a pond cross each other and create a complex pattern. So electrons are waves? But they arrive as clicks, individual lumps. We never detect a piece of an electron. It's always whole. Here's the situation. Electrons arrive like particles, but they arrange themselves like waves. Okay, maybe they're bumping into each other somehow, interfering with each other on the way. So let's slow everything down. We send 1 electron at a time. Shoot one, wait for it to arrive, then shoot the next. They never meet. We do this, very patient, one by one. Same pattern, stripes, interference. Each electron is interfering with itself. What does that even mean? Well, maybe the electron splits in half, goes through both slits and meets itself on the other side. Let's check. We put a little detector at the slits to see which way each electron goes, and we watch. Every single electron goes through one slit or the other. Never both. We catch it in the act. Left slit or right slit. It's a definite particle taking a definite path. But now we look at the pattern on the back wall. The stripes are gone. Just 2 clusters, like tennis balls. Exactly what you'd expect from particles that go through one doorway or the other. So when we don't look at which slit the electron goes through, we get interference. When we do look, the interference disappears. Let me say that again because it sounds insane. The act of finding out which path the electron took changes the outcome of the experiment. Now you might think, well, our detector probably bumped the electron, disturbed it somehow. Physics involves interactions, right? So let's be gentler. Let's use the softest possible way to detect the electron. We try this, and here's what Heisenberg discovered. There is no gentle enough way. If your detection method can actually tell you which slit the electron went through, it will always disturb things enough to destroy the interference. And if your method is too gentle to disturb anything, it's also too gentle to give you the information. You cannot have both. You cannot know the path and keep the pattern. Nature doesn't allow it. This isn't about our technology being bad. It's not that we need better instruments. This is fundamental, built into the fabric of reality. The electron doesn't have a definite path until you look. And when you look, you force it to choose. But wait, that's strange. Before we looked, where was the electron? Did it go through both slits? Did it go through neither? Did it take every possible path at once? Here's the answer, and you're not going to like it. We don't know. And more importantly, the question might not even make sense. See, we grew up in a world of tennis balls and doorways. Things have positions. They take paths. They're somewhere. That's intuition. That's common sense. But common sense comes from everyday experience. And everyday experience is made of big things, billions and billions of atoms stuck together. At that scale, quantum weirdness averages out. You don't see it. But down at the level of single electrons, single photons, the rules are different. Our intuition doesn't apply. The words we use, like path and position and where is it, Those words might not even mean anything down there. So when someone asks, but which slit did the electron really go through? The only honest answer is, if you don't measure it, the question has no answer. Not, we don't know the answer. The question itself doesn't apply. That's quantum mechanics. That's what nature is actually like. And if you don't like it, well, nature doesn't care. Every way an event can happen, we draw an arrow for it. The arrow has a length, and it points in some direction. And here's the rule. To get the probability of something happening, you take the final arrow and square its length. So an arrow of length 0.4 means a probability of 0.16, 16%. Simple. But here's where it gets interesting. When something can happen in more than one way, like an electron going through the left slit or the right slit, we don't add the probabilities, we add the arrows first. And arrows are sneaky things. See, if you have two arrows pointing the same direction, you put them head to tail and get a longer arrow. Big probability. But if they point in opposite directions, they cancel out. Small probability, maybe zero. That's interference. That's why we see stripes. The arrows for went through left slit and went through right slit sometimes point together, sometimes point opposite, depending on where on the screen you're looking. But when you detect which slit the electron went through, you're not adding arrows anymore. Now you know it went through one specific slit, so you calculate the probability for that slit alone. No arrows pointing opposite, no cancellation, no interference. The math is actually simple. What's hard is accepting what the math means. But what are these arrows really? What do they represent? Nothing. They don't represent anything physical. You can't go find an arrow attached to an electron. It's just a calculation tool, a recipe for getting the right answer. We call them probability amplitudes. Fancy name, but really just arrows. And here's the strange part. The arrows involve imaginary numbers, square root of -1, numbers that don't exist on any ruler. Yet when we square them to get probabilities, we always get regular positive numbers, real things, things we can measure. So reality is built on something we cannot directly see, using numbers that cannot directly exist to predict outcomes that are merely probable. Welcome to quantum mechanics. Now you might wonder, why does nature work this way? What's the deeper explanation? There isn't one. Nobody knows why nature uses probability amplitudes. Nobody knows why the arrows work. We know that they do. Every experiment we've ever done confirms it. But the mechanism behind it, the reason, we have no idea. And honestly, that's okay. Science doesn't always answer why. Sometimes it just answers how. And if you keep pushing, why this, why that, eventually you reach bedrock, the place where the only honest answer is, that's just how nature is. Take it or leave it. So, let me give you an example. Let's go back to something simpler than electrons. Let's talk about light hitting a piece of glass. You shine light at glass. Some reflects, some goes through. About 4% reflects from the front surface, 96 goes through. Simple question. Which photons reflect and which go through? Answer, nobody knows. Can't be predicted. Each photon has a 4% chance of reflecting, 96% chance of going through. That's all we can say. Now add a second surface, the back of the glass. Now photons can bounce off the front or the back. You'd expect about 8% total reflection. 4 from the front, 4 from the back. No. It depends on how thick the glass is. Some thicknesses give you 16% reflection. Some give you 0. 0. The back surface somehow turns off the reflection from the front surface. How do we calculate this? Arrows. We draw one arrow for reflects off front surface. We draw another arrow for reflects off back surface. But here's the key. The direction each arrow points depends on how far the photon traveled. Imagine a little clock that spins as the photon moves, very fast, thousands of rotations per inch for visible light. When the photon reaches a surface, wherever the clock hand is pointing, that's the direction of the arrow. For the front surface, the clock points one direction. For the back surface, the photon traveled a bit farther, so the clock points a different direction. Now we add the arrows. If they point the same way, big arrow, lots of reflection. If they point opposite, they cancel. No reflection. The thickness of the glass determines how much the clock rotates between the front and back surface. So the thickness determines whether the arrows add or cancel.
All right. So we've seen that nature is strange. Electrons behave in ways that make no sense to our everyday intuition. But now I want to show you something even more fundamental. Something that explains why you're sitting in a chair right now instead of falling through it. The uncertainty principle. You've probably heard this phrase before. Most people think it means our instruments aren't good enough. That if we just built better equipment, we could measure things more precisely. No, that's completely wrong. The uncertainty principle is not about bad instruments. It's about nature itself. It's a fundamental limit built into reality. Here's what it says. You cannot know both the position of a particle and its momentum at the same time. Not because you're clumsy, not because your measuring device is cheap, but because the particle doesn't have both a definite position and a definite momentum at the same time. Let me make this concrete. Suppose you want to know exactly where an electron is. You confine it to a very small region. You trap it in a tiny box. Now you know its position very well. But here's the cost. The momentum becomes uncertain. The electron starts moving faster. It has to. The more precisely you pin down where it is, the more wildly its momentum fluctuates. And it works the other way, too. If you know the momentum very precisely, you know exactly how fast the electron is moving, then its position becomes fuzzy. It could be anywhere. The product of these two uncertainties can never be smaller than a certain number, a very small number, Planck's constant. But it's not zero. There's always some uncertainty left over. So, why does this happen? Remember the arrows? Remember how we said particles behave like waves in some sense? Here's the connection. Think about a wave, a perfect wave that goes on forever, same height, same rhythm, repeating to infinity. That wave has a very definite wavelength. You can measure it precisely. But where is the wave? It's everywhere. It goes on forever. There's no specific location. Now think about a short burst, a pulse, just one little bump, and then nothing. Where is it? Easy. It's right there in that small region. You know its position, but what's its wavelength? Hard to say. It's not really repeating. You can't measure a wavelength from a single bump. It doesn't have a definite wavelength. See the trade-off? A wave that's spread out everywhere has a definite wavelength, but no definite position. A wave that's concentrated in one spot has a definite position, but no definite wavelength. And in quantum mechanics, wavelength is connected to momentum. They're related. Short wavelength means high momentum. Long wavelength means low momentum. So this trade-off between position and wavelength becomes a trade-off between position and momentum. It's not mysterious, it's just how waves work. Any engineer who deals with sound waves or radio signals knows this. If you want a precise frequency, you need a long signal. If your signal is short, the frequency is fuzzy. Quantum mechanics just tells us that particles have this wave nature, and waves have this built-in trade-off. But here's where it gets really interesting. This explains why atoms exist. Think about it. An atom is a nucleus, positive charge, with electrons around it. Opposite charges attract. So why doesn't the electron just fall into the nucleus? Why doesn't it spiral down and crash? Classical physics has no answer. In classical physics, the electron should radiate energy as it orbits, lose speed, spiral inward, and collapse onto the nucleus in a tiny fraction of a second. Every atom should collapse. Matter shouldn't exist. But matter does exist. You exist. The chair you're sitting on exists. Why? The uncertainty principle.
If the electron fell into the nucleus, we would know exactly where it is, right there at the center. Position very precise. But then its momentum becomes very uncertain. The electron would be moving incredibly fast, flying off in random directions. It would have enormous kinetic energy.
So the electron can't stay at the nucleus. It gets pushed out by its own uncertainty. And it can't stay too far away either, because the electrical attraction keeps pulling it back. There's a balance, a compromise. The electron settles into a region that's not too small and not too big. Small enough to feel the attraction of the nucleus, big enough to keep the momentum under control. That region is about 1/10 of a billionth of a meter, and that's the size of an atom. Let me say that again. The size of atoms, the fundamental scale of chemistry, biology, everything around you, comes from the uncertainty principle. Without quantum mechanics, there are no atoms. Without atoms, there are no molecules. Without molecules, there's no chemistry. Without chemistry, there's no life. You exist because the uncertainty principle won't let electrons collapse into nuclei. And there's more. This is why you don't fall through the floor. When you stand on the ground, the atoms in your shoes get close to the atoms in the floor. If you try to push them closer together, squeeze them into a smaller space, the electrons resist. Their positions would become more certain, which means their momenta would become more uncertain. They'd start moving faster. They'd push back. That's what solid mean. That's what hard mean. The resistance of matter to being compressed is a quantum mechanical effect. In classical physics, the best arrangement of positive and negative charges would be all of them sitting on top of each other. Everything collapsed to a point, but quantum mechanics says no. You can't confine particles to a small space without paying the price in momentum. So the next time you sit in a chair and it holds you up, that's quantum mechanics. That's the uncertainty principle, doing its job, keeping you from falling through to the center of the earth. Now here's something else that classical physics got completely wrong. Energy. In the everyday world, energy seems continuous. You can have any amount you want. You push a car a little, it goes a little. Push harder, it goes more. Smooth, gradual, any value is possible. But in the atomic world, energy comes in steps, specific amounts, like a staircase, not a ramp. Think of it this way. Imagine you're climbing a hill. In classical physics, you can stop at any height, halfway up, a third of the way, any fraction you like. But atoms are different. Atoms are like a building with floors. You can be on the first floor, the second floor, the third floor, but you cannot stand between floors. Those in-between positions simply don't exist. An electron in an atom can have certain energies, specific values, not anything in between. Why? Because the electron is confined. It's trapped in the space around the nucleus, and confined waves can only vibrate in certain ways. Think of a guitar string. It's fixed at both ends. When you pluck it, it vibrates, but it can't vibrate any way it wants. It has a fundamental frequency, the lowest note. Then it has harmonics, higher notes at specific frequencies. You don't get a continuous range, you get specific notes. Same with electrons in atoms. The electron wave has to fit around the nucleus in a certain way. Only certain patterns work, and each pattern has a specific energy. We call these energy levels, and this explains something beautiful: light. When an atom is in a high energy level, it can drop to a lower one, but it has to lose that energy somehow. Where does it go? It comes out as light, a photon. And here's the key. The photon carries exactly the energy difference between the two levels. Not approximately, exactly. Since the energy levels are specific, the energy of the photon is specific. And the energy of a photon determines its color. Blue light carries more energy than red light. So each type of atom produces specific colors of light, definite frequencies, sharp lines. Hydrogen produces certain colors. Helium produces different colors. Sodium produces that yellow-orange glow you see in some street lamps. So, if you look at the light from a distant star through a prism, spreading it into a rainbow, you see dark lines, specific colors missing.
Those are the fingerprints of atoms. Each element absorbs and emits specific frequencies. By reading those lines, we can tell what stars are made of billions of miles away, all because energy in atoms comes in steps, not smooth gradients. And here's something that puzzled people for decades. Why those specific steps? Why those particular energy levels? Now you know. The uncertainty principle, the wave nature of particles. Confined waves can only have certain patterns. Those patterns determine the allowed energies. Everything connects. Now let me tell you about something even stranger. The quantum world has rules that seem completely arbitrary, ridiculous even. For example, electrons refuse to be in the same state. What does that mean? If you have an atom with many electrons, they don't all crowd into the lowest energy level. That would be the most economical arrangement, right? Everyone on the ground floor? But no. Only 2 electrons can occupy each level, and those 2 have to be spinning in opposite directions. After that, the level is full. The next electron has to go to a higher floor. This is called the Pauli exclusion principle, and nobody knows why it's true. It just is. But without it, chemistry wouldn't exist. Think about it. If all electrons could pile into the lowest level, every atom would behave the same way. Carbon would be like oxygen, would be like iron. All the electrons huddled at the bottom. No variety. But because electrons have to spread out into different levels, different atoms have different arrangements. Different arrangements mean different chemical behaviors. Carbon acts like carbon. Oxygen acts like oxygen. Iron acts like iron. The periodic table, all of chemistry, exists because electrons refuse to share the same state. And this same principle explains why matter has volume, why atoms take up space, why you can't squeeze things indefinitely. The electrons in the outer parts of atoms cannot fall inward because those inner levels are already occupied, full, no vacancy. So matter is rigid. Tables are solid. You don't fall through floors. It's strange, isn't it? The rules seem arbitrary. Why 2 electrons per level? Why not 3? Why not 10? I don't know. Nobody knows. These are the rules nature plays by. We discovered them by doing experiments, by looking carefully at how atoms actually behave. The rules work. They give predictions that match reality to incredible precision. But the deep reason behind them? Still a mystery. And maybe there is no reason. Maybe asking why at this level is like asking why the rules of chess are what they are. They just are. You learn them. You play the game. Nature has rules. Our job is to discover them, whether they make sense to us or not. So where does all this leave us? We started with a simple experiment, electrons going through 2 slits, and we ended up having to throw away almost everything we thought we knew about reality. Particles don't have definite positions until you look. They don't take definite paths. They exist as clouds of probability, described by arrows that we add together. The act of observation changes the outcome, and there are fundamental limits to what can be known, not because we're ignorant, but because nature itself is fuzzy at the bottom. This bothers people. It bothered a lot of very smart physicists. Some of them spent their whole lives trying to find a way around it, trying to prove that underneath all this uncertainty, there must be some hidden machinery, some deeper layer where things make sense again, where particles have real positions and real paths that we just can't see. So far, every attempt has failed. Every experiment we've done confirms the quantum picture. The fuzziness is real. The probabilities are fundamental. There's no hidden clockwork underneath. Now, you might ask, if particles don't have definite properties until we measure them, what's really going on? What is reality, actually? Honest answer? We don't know. And here's something that might bother you even more. The theory doesn't tell us. Quantum mechanics is a set of rules for calculating probabilities. It tells you what you'll observe when you do an experiment. It doesn't tell you what's happening when you're not looking. Some people say the particle is in many states at once until you observe it. Some say there are many parallel worlds where every possibility happens. Some say the question itself is meaningless. We should only talk about what we can measure. These are interpretations, philosophy. They all give the same predictions. There's no experiment that distinguishes between them. So physicists mostly shrug and say, use whatever picture helps you think, as long as you get the calculations right. But let me tell you what we do know for sure. The theory works. Quantum electrodynamics, the theory of how light and electrons interact, has been tested to extraordinary precision. We can calculate certain quantities to 10 decimal places, and the experiments match. 10 decimal places. That's like measuring the distance from one city to another and getting it right to the width of a hair. No other theory in the history of science has been tested this precisely, and quantum mechanics passes every test. So whatever is going on underneath, whatever reality really is, the rules we've discovered are correct. They work, they predict, they explain. And look what they explain. Why atoms exist, why matter is solid, why different elements have different properties, why the sun shines, why chemistry works, why you can read these words with eyes that evolved over millions of years in a universe built on quantum rules. Everything around you, everything you've ever touched, seen, or experienced is made of particles obeying these strange laws. And here's the thing, you don't notice it. Day to day, the world seems perfectly normal. Objects have positions, things take definite paths. Cause leads to effect in sensible ways. Why don't we see the quantum strangeness? Because we're big. We're made of billions and billions of atoms. And when you have that many quantum particles together, the weird effects average out. The interference patterns get so fine that you can't detect them. The uncertainties get so small compared to everyday scales that they disappear. It's like this. Each atom is doing something strange, but they're all doing strange things in different ways. And when you add it all up, it looks smooth, it looks classical, it looks normal. The quantum world is always there, underneath, but it's hidden by sheer numbers. So, what have we learned? We learned that nature is not obligated to make sense to us. Our brains evolved to track fruit and avoid predators, to deal with medium-sized objects moving at medium speeds. We didn't evolve to understand atoms. We didn't evolve to visualize probability amplitudes. And yet, somehow, we figured it out anyway. That's the amazing part. Not that nature is strange, but that we, these collections of atoms, these temporary patterns of matter, managed to discover the rules. We built detectors and did experiments and wrote down equations. And the equations work. We don't know why the rules are what they are. We don't know what's really happening when we're not looking. We don't have a satisfying picture that fits human intuition. But we have something better than intuition. We have a theory that predicts what will happen. And when we do the experiments, it's right. Every time. That's physics. That's quantum mechanics.
When people hear the word mass, they usually think of heaviness. Something massive feels difficult to lift, difficult to move, difficult to stop. That intuition points in the right direction. But in physics, mass plays a more precise role than everyday language suggests. Mass is about resistance to change in motion. Push an empty shopping cart and it responds immediately. Load it with groceries and the same push produces a much smaller effect. Nothing about the push changed. Nothing about the floor changed. What changed was the amount of mass that had to be persuaded to move differently than it was moving before. Mass measures how strongly matter resists acceleration. This resistance appears in every situation where motion changes. Starting to move, stopping, turning, or speeding up all require effort when mass is involved. The greater the mass, the more effort is required to produce the same change. Once an object with mass is moving, it does not easily give up that motion. Once it is at rest, it does not easily begin moving. Motion demands a cause, and mass determines how large that cause must be. This already tells us something important. Mass does not describe how fast something moves. Two objects can travel side by side at the same speed and respond very differently when pushed. Mass cares about change, not motion itself. Now gravity enters the picture, and everyday experience begins to blur ideas together. On Earth, objects with more mass feel heavier because gravity pulls on mass. More mass means a stronger gravitational pull, which we experience as greater weight. Because gravity is always present in daily life, mass and weight often get treated as the same thing. Physics keeps them distinct. Mass belongs to the object itself. Weight belongs to the interaction between that object and a gravitational field. Take the same object to the moon, and the weight decreases. The mass does not. The resistance to acceleration remains exactly the same. This separation matters because gravity is only one way mass reveals itself. There is a deeper fact hiding here. The quantity that determines how strongly gravity pulls on an object is exactly the same quantity that determines how strongly that object resists acceleration. Experiments show this equivalence with extraordinary precision. No adjustments are needed. The numbers match every time. Because of this, mass links motion and gravity into a single concept. It sets the scale for how objects respond to forces and how they influence one another. Wherever mass appears, it defines how difficult change will be. Without announcing itself, mass shapes how the physical world behaves. And once you accept that mass measures resistance to change, the picture widens in an unexpected way. Up to now, mass has sounded like a property objects carry around with them, something internal, something local. But mass does more than resist acceleration. It also participates in the structure of the universe itself. To see this, forget objects for a moment and think about motion in empty space. If there were no mass anywhere, space and time would behave like a simple grid. Straight lines would stay straight. Clocks would tick the same way everywhere. Motion would follow predictable paths, unless something intervened. Introduce mass, and that picture no longer holds. Mass affects how objects move, not only by responding to forces, but by influencing the very arena in which motion takes place. In modern physics, space and time are not separate backgrounds where events happen. They are joined into a single structure called space-time, and mass plays a central role in how that structure behaves. This sounds abstract, so let's ground it. Imagine two nearby clocks, one placed on the ground and one lifted higher. Even before worrying about motion, they do not measure time the same way. The clock closer to a massive object runs differently from the one farther away. This difference is not a malfunction, it is a physical effect. Time itself depends on the presence of mass. The same happens with distance. Straight paths bend near massive objects. Light, which has no mass of its own, still follows curved routes when it passes near large masses. Nothing pushes it sideways, it simply follows the geometry shaped by mass. Mass does not pull on space and time like a hand tugging on fabric. Instead, mass and energy determine how space-time is arranged, and objects move according to that arrangement. Motion follows the available geometry. This is why gravity looks the way it does. Rather than thinking of gravity as a force acting at a distance, physics treats it as the result of mass influencing space-time and objects moving accordingly. A planet orbiting a star is not being dragged around by an invisible tether. It is following the most natural path available in the space-time shaped by the star's mass. This explains something that once seemed mysterious. Objects fall at the same rate, regardless of their mass, as long as other effects are negligible. The resistance to acceleration and the gravitational influence scale together. Because of that balance, motion under gravity becomes independent of the object's own mass. Mass shapes space-time. Objects respond to space-time. The result is what we experience as gravity. Now pause and connect this back to the earlier idea of resistance to change. An object with mass resists changes in motion. Space-time with mass resists being arranged in a flat, uniform way. In both cases, mass introduces rigidity. It sets how difficult it is for motion and geometry to behave differently than they already do. This brings us to an important point that often causes confusion. Mass is not the same as energy, but they are closely related. Energy contributes to space-time in much the same way mass does. Heat, motion, and radiation all influence space-time, though mass tends to dominate in everyday situations because it is concentrated. That famous equation connecting mass and energy is not about explosions or technology. It is a statement that mass is one way energy can exist, and that energy, in any form, participates in shaping space-time. So mass is no longer just about heaviness or resistance. It becomes part of the reason space and time behave the way they do. At this stage, it helps to let go of the idea that space-time is a thing sitting underneath the universe. It behaves more like a set of relationships, how distances are measured, how durations pass, how paths are traced. Mass influences those relationships directly, and this influence is not optional. You cannot turn it off. Any amount of mass, no matter how small, contributes. The effects only become noticeable when the mass is large or concentrated enough, but the rule applies everywhere. What began as a measure of how hard it is to push something now reveals itself as a measure of how strongly matter participates in the structure of reality. Mass tells space-time how to behave, and space-time tells matter how to move. Once you see that connection, mass stops being a simple property of objects and becomes a key player in the architecture of the universe. And once mass is seen as something that participates in space-time itself, another question becomes unavoidable. Where does mass come from? Up to this point, mass has behaved like a given. Objects have it. It resists acceleration. It influences space-time. But physics does not stop at description. It keeps asking, what mechanisms make those descriptions true? Here is the surprising answer. Most of the mass you encounter every day does not come from the intrinsic mass of particles. Take a proton, one of the building blocks of atomic nuclei. It is made of quarks, and quarks do have mass. But if you add up the masses of the quarks inside a proton, you get only a small fraction of the proton's total mass. The majority comes from something else entirely. It comes from energy. Inside the proton, quarks move at enormous speeds and interact through strong forces. The energy stored in that motion and interaction contributes to the proton's mass. According to the rules of physics, energy and mass are deeply linked, so confined energy shows up as mass. This means that much of what you call matter is energy held in place by interactions. Mass, in practice, measures how much energy is tied up in a system in a way that resists change. This idea scales upward. The mass of everyday objects comes largely from the mass of protons and neutrons, which themselves owe most of their mass to internal energy. Even solidity, the feeling that objects are rigid and substantial, comes from electromagnetic interactions between atoms, not from mass alone. Mass is not a simple substance filling space. It is an expression of how energy is organized and constrained. Now this leads directly to another common confusion. If energy can appear as mass, and mass influences space-time, does that mean mass and energy are the same thing? Not exactly. They are different ways of describing the same physical content, depending on context. When energy is localized and behaves like inertia, we describe it as mass. When it moves freely or spreads, we describe it as energy. The distinction is practical, not fundamental. This explains why light, which has no mass, still carries energy and momentum and can influence space-time. It does not resist acceleration in the same way matter does, but it still participates in the overall structure. Mass becomes a special case, energy that is bound in such a way that it resists changes in motion and position. Now return to inertia, the resistance to acceleration that started this discussion. In classical physics, inertia simply exists. Objects resist acceleration because they do. Modern physics digs deeper and asks what gives particles that resistance in the first place. Here another piece enters the picture: fields. Particles do not exist in isolation. They exist in the presence of fields that fill space. One of these fields plays a special role in determining mass. Interaction with this field gives certain particles their intrinsic mass. Without that interaction, many particles would behave as if they were massless, moving at the speed of light. Mass, at the most basic level we know, emerges from interaction, not isolation. This reinforces a theme that keeps appearing. Mass is relational. It expresses how strongly something is tied into the rest of the physical world. The more tightly energy is bound, or the more strongly a particle interacts with relevant fields, the more mass it exhibits. Mass is not a label attached to matter. It is a measure of participation. Now consider how this affects motion at very high speeds. As objects move faster, changing their motion becomes increasingly difficult. Adding the same amount of energy produces smaller changes in speed. This is not because the object is gaining mass in a literal sense, but because space-time itself imposes limits on how motion can change. The resistance to acceleration increases as speed approaches the maximum allowed speed. Once again, mass and space-time work together. What begins as inertia at low speeds becomes a geometric constraint at high speeds. This shows that mass is deeply connected to limits. Limits on acceleration, limits on energy concentration, limits on how space-time responds, and limits are often where understanding becomes sharpest. Now bring all of this back to scale. At small scales, mass arises from particle interactions and confined energy. At human scales, it governs how objects respond to forces and gravity. At cosmic scales, it shapes space-time and determines how galaxies form, how stars orbit, and how light travels across the universe. The same concept applies everywhere, only the language changes. This universality is what makes mass such a powerful idea. It appears in mechanics, thermodynamics, quantum theory, and relativity without changing its role. The equations look different, but the meaning persists. Mass measures how strongly something resists change and how strongly it influences the structure around it. And this brings us to an important correction to everyday intuition. Mass does not make things want to stay still. Objects do not prefer rest. Motion and rest are relative concepts. What mass does is resist changes in motion, regardless of the current state. Rest and uniform motion are treated the same by physics. This is why astronauts floating in space still have mass. They are weightless, not massless. They resist being pushed just as much as they would on Earth. The absence of weight does not remove inertia. Weight is local, mass is universal. Once this distinction is fully absorbed, many confusions dissolve. Falling objects, orbiting planets, floating astronauts, and bending light all follow from the same idea applied in different settings. Mass becomes less mysterious, not more. It is no longer a substance hidden inside matter. It is a measure of how matter and energy respond to the rules of motion and space-time. And with that understanding in place, mass stops being a word you memorize and becomes a concept you can use, one that explains why the universe reacts the way it does whenever anything tries to change. And at this point, mass can finally be treated as a fully connected idea rather than a collection of separate facts. Mass is not just resistance to acceleration. It is not just what gravity acts on. It is not just a number listed next to particles in a table. Mass is the quantity that ties together motion, gravity, energy, and space-time into a single framework that works at every scale we can test. When physicists use mass in an equation, they are not inserting a vague property. They are specifying how strongly a system resists changes in motion, how much it contributes to space-time geometry, and how much energy is locked into a form that behaves inertially. One number plays all of these roles because experiments show they are inseparable. This is why mass appears in so many places without changing meaning. In mechanics, it sets how force produces acceleration. In gravity, it determines how objects influence one another's motion. In relativity, it contributes to how space-time is shaped. In particle physics, it reflects how particles interact with underlying fields. Different theories, same role. Mass is consistent across contexts. That consistency allows physicists to trust it. When calculations involving mass agree across experiments as different as particle collisions, planetary motion, and atomic measurements, the concept earns its place as fundamental. It also explains why mass cannot be defined in isolation. You cannot measure mass without interaction. You measure it by pushing, pulling, colliding, orbiting, or observing motion under gravity. Mass reveals itself only through relationships. It is not a private attribute of an object. It is how that object participates in physical processes. This relational nature becomes especially clear when mass is absent. Particles with no mass still carry energy and momentum, but they do not resist acceleration in the same way. They cannot be brought to rest. Their behavior marks the boundary of what mass changes. Comparing massive and massless systems highlights exactly what mass contributes and what it does not. Mass introduces inertia. Mass introduces gravitational influence. Mass introduces limits on how motion responds to added energy. Remove mass and those features disappear. At the same time, mass does not act alone. Energy, momentum, and space-time geometry work together. No single concept explains everything. Mass matters because it connects these ideas in a way that remains valid whether you are studying atoms, engines, planets, or galaxies. This is also why mass is not something physics expects to be replaced or discarded. Future theories may explain its origin more deeply or describe it in new language, but they will still need a quantity that plays the same role. Whatever name it goes by, it will have to resist acceleration, contribute to gravity, and participate in space-time. Those requirements are not optional. They come directly from observation. So when someone understands mass in physics, they are not just learning a definition. They are learning how physicists think about change. They learn why motion responds the way it does, why gravity behaves universally, and why energy cannot be rearranged without consequences. Mass becomes a practical tool for reasoning. It allows you to explain why heavy and light objects respond differently to forces, why astronauts float yet still resist pushes, why stars bend the paths of light, and why most of the matter around you owes its mass to energy bound by interactions rather than to tiny particles acting alone. Once mass is understood this way, it stops being confusing. It becomes predictable. It becomes something you can explain without memorizing phrases or relying on vague analogies. Mass is how physics keeps track of resistance to change and influence on space-time using one quantity that works everywhere it is applied. And that is why mass remains one of the central concepts in physics, not because it is mysterious, but because it is reliable.
Every time you seek approval, your worth becomes a hostage to someone else's opinion. And the strange thing is, the more you try to please the world, the more the world ignores you. Life begins to lose its brightness when you live to be seen instead of living to understand. Now imagine just for a moment That all the energy you spend trying to be accepted was redirected into learning, into exploring, into understanding how things truly work. Imagine the power that would have. You'd start to see the hidden beauty in simple things, in sound, in light, in ideas, in people. Because true genius isn't born from the desire to be admired, but from curiosity, that pure restlessness that makes you want to discover why things are the way they are. And when you dive into that curiosity, life starts to flow in a way that no ambition can ever reproduce. The truth is, the pursuit of recognition is a trap disguised as motivation. It pushes you to run faster, to work harder, to achieve more, yet it never lets you rest. It's a bottomless pit, and you know what's at the bottom of that pit? Nothing but emptiness. The emptiness of someone who lived to be remembered instead of living to understand. So listen closely. Living for the love of understanding is the only path that truly sets you free, because the pleasure of discovering is the reward itself, and the one who learns for the joy of learning never needs applause. Pay attention to me now, because what I'm about to tell you might completely change the way you see life. You've spent far too long trying to be recognized, trying to prove something to others, and without realizing it, you became a prisoner of that need. But let me tell you this. Most of the people who seem to be winning are actually losing silently. They collect titles, possessions, praise, yet they lose something invisible, their inner freedom. They live like actors on a stage, playing a role the world wrote for them. But you know the problem? When the curtain falls, there's only silence. And in that silence, the question no one wants to face appears. Why am I doing all this? If your reason is to be recognized, you'll never rest. Because recognition is volatile. It shifts with people's moods, with trends, with the tides. One day they applaud you, the next they forget you. And if your worth depends on that, you're doomed to rise and fall with the world around you. But when you do something for the simple joy of understanding, something inside you changes. Suddenly time moves differently. You stop chasing, and you start being guided by something deeper. Curiosity. Curiosity is the engine of life. It turns boredom into discovery, pain into learning, chaos into meaning. When you follow that energy, you no longer need recognition, because the pursuit itself becomes fulfilling. It's the joy of understanding what lies behind things, of seeing how everything connects. That is true power. When you learn for the love of comprehension, the entire world opens before you. You stop being an actor, and you become the author. And for the first time, life starts to make sense. But to reach that point, you must do something few ever dare. Stop trying to be someone and start trying to understand something. The difference seems small, but it's enormous. The first path enslaves you. The second one sets you free. Pay attention to me now, because I want to take you to a place where very few have the courage to look. People think freedom means being able to do whatever they want, but that's just the reflection of modern ignorance. True freedom is being able to think whatever you want, to doubt what you've been taught, and to allow yourself not to know. A mind that seeks recognition is enslaved by certainty. A mind that seeks understanding is free to explore. Do you want to know what truly destroys genius? The need to appear intelligent. The person who tries to look smart for others will never be truly intelligent, because they're focused on displaying, not discovering. Genius is born the moment you abandon the desire to be special and embrace the joy of uncovering the obvious. Think about it. Everything you know was once obvious to someone who had the courage to look closely. The difference between the mediocre and the brilliant doesn't lie in talent. It lies in genuine curiosity. The mediocre wants to be right. The brilliant wants to learn, even if it means stripping away their own vanity. And here's the irony. The more you care about what others think, the less you actually think for yourself. A curious mind is like a child taking apart a toy just to see what's inside. It doesn't crave status. It doesn't want applause. It wants the mystery. It wants the why. And that's what keeps the inner fire alive. The sincere desire to understand the world before the world understands you. Life becomes light when you realize you don't need to impress anyone. You begin to do things for the simple pleasure of seeing what happens. And strangely enough, that's when everything starts to work. When you stop chasing results, the results begin to chase you. Because the universe responds to genuine curiosity, not to empty ambition. The secret isn't to be recognized, it's to be so deeply immersed in the process that recognition becomes irrelevant. The reward lies in the very act of understanding. And those who live that way exist in a state of freedom that money and status could never buy. Now imagine something uncomfortable yet necessary. What if most of human suffering didn't come from lack, but from excess? The excess of wanting, proving, showing. The world taught you that ambition is a virtue, but forgot to warn you that blind ambition is poison. You run, you exhaust yourself, you achieve, and when you finally arrive where you always wanted to be, you realize there's no one there, not even you. People confuse purpose with performance. They crave meaning, yet spend their days trying to win a race they never chose to run. They long for freedom, yet choose paths that chain them. The pursuit of status, applause, validation. And the worst part? They believe they're evolving, when in truth, they're only moving further away from themselves. Let me tell you something few have the courage to face. Success without understanding is just another form of failure. Because if you don't understand what you're doing, success becomes an accident. And accidents don't set you free. They enslave you. When you act only for the result becomes your master. But when you act for the love of understanding, you are in control, and life begins to flow again. There is no purer pleasure than the pleasure of truly understanding. When you truly understand, there's no need to compete. There's no envy, no rush, no comparison. There's only a curious silence, that rare moment when everything makes sense for just a few seconds, and you feel part of something far greater than ambition itself. The problem is most people want to understand the world, but they don't want to understand themselves. They crave answers but can't stand questions. And that's why they live tired, anxious, and empty. Because they try to fill what is spiritual with what is material. They try to buy, conquer, or prove what can only be understood. Life is not a podium. It's a laboratory. You're not here to win. You're here to discover. And when you understand that, you realize the whole game changes. It stops being a competition and becomes an investigation. Every mistake becomes a clue. Every failure, a new hypothesis. And that's how you begin to free yourself. Not by winning, but by understanding. When a human being finally lets go of the need for recognition, something extraordinary happens. They are reborn. The mind becomes light. The heart becomes quiet. And for the first time, they begin to taste real freedom. Suddenly, fear disappears. The fear of failing, of being judged, of not being enough. Because now, none of that matters. You no longer live to prove. You live to experience. And in that moment, life starts to align with who you truly are. Opportunities appear. Ideas flow. The right people come closer. Because you stopped being a copy begging for acceptance and become an authentic source of energy and creation. Authenticity has a power the modern world has forgotten. When you are real, the entire universe seems to recognize you in a way applause never could. Life begins to conspire in your favor, because at last you're playing the right game, the game of growing from within. And everything that once seemed difficult begins to happen naturally, because when your focus shifts from appearing to understanding, you connect to the natural flow of things. You don't force, you simply are. Do you want to know what true peace feels like? It's waking up one day and realizing you don't need to impress anyone, that you are enough simply for being here, learning, failing, trying to understand. And from that moment on, every gesture, every word, every small discovery starts to have meaning. You begin to see beauty where you once saw routine. You begin to see purpose where you once saw haste. Likeness is born when vanity dies. And the pleasure of discovery becomes greater than any achievement. Life flows, not because you control it, but because you understand it. And once you understand, you no longer need to run. You realize that what truly matters is not what others think of you, but what the universe reveals when you finally choose to listen. Now write this in the comments. With conviction, I choose the freedom of understanding. This phrase will begin to reprogram your subconscious, reminding your mind every day of what truly matters. From today on, make yourself a promise. Live for the love of understanding, not for ambition. Stop chasing recognition and start seeking meaning. That is the key that changes everything. If this message touched you, like the video, subscribe to the channel, and turn on the bell because what's coming next will expand your mind even more. And remember, to understand is to be free, and the one who becomes free inspires the world without needing to say a single word.
You know, I've noticed something peculiar over the years. People come up to me and say they understand quantum mechanics, or they understand relativity. And when I ask them to explain it, they repeat the words back to me. Beautiful words, elegant phrases. But it's like they're reciting poetry in a language they don't speak. That's not understanding. That's something else entirely. Let me tell you what I mean, and maybe you'll recognize yourself in this. I certainly recognized myself when I was younger. When I was a student at MIT, I thought I was pretty smart. I could solve problems, pass exams, manipulate equations. I knew how to get the right answer. But there was a professor there, his name doesn't matter, who asked me something after class one day. He said, explain to me why, when you spin an electron, it takes 2 full rotations to come back to its original state, not 1. I started talking about spinors and group theory and mathematical properties. I used all the right words. He just looked at me and said, but do you know why? I didn't. I had no idea. I knew the mathematics, but I didn't understand the thing itself. And that embarrassed me more than any wrong answer ever could. That moment stuck with me, because I realized I'd been fooling myself. I'd been collecting facts and formulas like stamps in an album, but I hadn't been thinking about what they meant. I hadn't been asking the real questions. So I started doing something different. When I encountered something new, let's say, a principle in physics or mathematics, I would sit down and try to work it out from scratch, not by looking it up, not by memorizing what someone else said. I would ask, if I knew nothing except the most basic facts, could I figure this out? Sometimes I'd spend days on a single idea. I'd invent my own notation. I'd draw pictures. I'd make up little stories about particles or waves or whatever I was studying. Most importantly, I'd test myself. Could I explain this to someone who'd never heard of it before? If I couldn't, I didn't understand it. Simple as that. Let me give you an example. When I was working at Los Alamos during the war, we were doing calculations about the bomb. Serious work, life and death, really. And there were all these brilliant people there, Einstein, Bohr, Oppenheimer. I was just a kid. One day, someone presented a calculation about neutron diffusion. Very complicated, lots of integral equations. Everyone nodded. It looked impressive, but I had this nagging feeling that something was off. I couldn't shake it. So that night I went back to my desk and I thought, forget the fancy mathematics for a moment. What's actually happening here? We have neutrons. They're bouncing around. Some get absorbed. Some cause fissions. It's like a bunch of drunk people wandering through a city, randomly bumping into buildings. I drew a picture. I imagined following a single neutron on its journey. Where does it go? What happens to it? I thought about it in the simplest possible terms, like I was explaining it to a child. And you know what? I found an error, a small one, but it mattered. The fancy mathematics had hidden an incorrect assumption. Everyone had been so busy following the equations that nobody had stopped to ask, does this make physical sense? That taught me something crucial. Understanding isn't about sophistication. It's not about using the right jargon or impressing people with complex formulas. It's about being able to strip away all the decoration and see the naked truth underneath. Here's what I learned to do, and what I still do to this day. First, when someone tells me they understand something, I ask them, can you give me an example? Not the textbook example, a new one you just made up. Because if you really understand a principle, you can apply it to situations you've never seen before. If you can only repeat the examples you were taught, you've memorized, not understood. Second, I try to find the simplest possible way to think about something. I had a friend once who said, if you can't explain it to a 6-year-old, you don't really understand it. Now, I don't know if that's exactly true. Some things are genuinely complicated, but the spirit is right. Simplicity is a sign of understanding. Complexity is often a sign of confusion. I used to do this exercise. I'd take something from my field, let's say, the principle of least action, and I'd pretend I was explaining it to my little sister when she was young. No equations, no fancy terms. Just what's happening. Why does nature work this way? And here's the interesting part. When I did this, I almost always discovered something I hadn't noticed before. Some little detail, some connection. The act of simplifying forced me to actually think about what was going on, rather than just pushing symbols around on paper. Third, and this is important, I learned to be honest about what I didn't know. This is harder than it sounds. We all want to appear smart. We all want to have answers. But the truth is, there's so much we don't know, so much I don't know. When I was teaching at Caltech, students would ask me questions, and sometimes I'd say, I don't know, let's figure it out together. And we would, right there in class. I'd work through it out loud, making mistakes, backtracking, trying different approaches. Some of my colleagues thought this was undignified. How can a professor admit he doesn't know something? But the students learned more from watching me struggle with a problem than they ever learned from watching me present a polished solution, because they saw how thinking actually works. It's messy. It's uncertain. It involves a lot of wrong turns and dead ends. Now, you might be wondering, isn't this inefficient? Shouldn't we just learn from experts, accept what they tell us, and build on top of that? Well, yes and no. Of course we stand on the shoulders of giants. Of course we don't need to rederive all of physics from first principles every time we want to solve a problem. That would be absurd. But there's a difference between accepting something provisionally and accepting it blindly. When I learn something from a book or a paper, I accept it as probably true. These people know more than me. They've done the work, but I hold it lightly. I keep asking, does this make sense? Does it fit with everything else I know? Could there be another explanation? I remember reading about the Wheeler-Feynman absorber theory. Well, I worked on it, actually, with John Wheeler. We had this idea about radiation and time symmetry. Very elegant mathematically, but there was something about it that bothered me. I couldn't put my finger on it, so I kept poking at it. I'd think about it while I was walking, while I was eating. I'd imagine different scenarios, different experiments. And eventually, I realized the theory made predictions that didn't quite match reality in certain extreme cases. The mathematics was beautiful, but nature didn't care about our mathematics. That's the thing. Nature is what it is. Our job isn't to make up pretty theories and force nature to fit them. Our job is to look at nature carefully, honestly, and try to understand what it's telling us. Let me tell you what this looks like in practice, because I think that's what you really want to know. When I encounter something new now, a paper, an idea, a problem, I go through a process. It's not formal. I didn't write it down as a method. But if I had to describe it, here's what I do. I start by asking, what does this really say? I try to state the idea in the simplest possible terms, in my own words, not the author's words, mine. If I can't do that, I don't understand it yet. Then I ask, what would happen if this were true? What are the consequences? I try to work out predictions, simple cases, examples. I play with the idea like a toy. I turn it over in my mind, look at it from different angles. Next, and this is crucial, I ask, what would convince me this is wrong? What evidence would I need to see to reject this idea? Because if I can't imagine anything that would prove it wrong, then I'm not really thinking about it critically. I'm just believing it. Finally, I try to connect it to other things I know. Does it fit? Does it contradict something else I believe to be true? If there's a contradiction, maybe I'm misunderstanding something. Or maybe one of my beliefs is wrong. Either way, I need to figure out which. This process, it takes time. It's not fast. But here's what I've discovered. When I do this, I actually remember things. They stick, because I haven't just memorized them, I've understood them. They become part of how I think about the world. You know what's funny? People sometimes call this the Feynman technique, like I invented something. I didn't invent anything. This is just thinking, real thinking. The kind of thinking that children do naturally before we train it out of them. Watch a child learn about the world. They don't memorize. They experiment. They ask why over and over. They're not satisfied with answers that don't make sense. They want to understand. Somewhere along the way, we lose that. We learn that there are right answers and wrong answers, and the goal is to know the right answers. We learn that understanding is measured by grades and test scores. We learn to be afraid of saying, I don't know. But real understanding, the kind that matters, the kind that lets you do something new, doesn't come from memorizing right answers. It comes from wrestling with questions, from being confused and sitting with that confusion until something clicks, from trying, failing, and trying again differently. I spent my whole career around people who could quote theorems and recite proofs. Very smart people. But the ones who actually contributed something new, the ones who saw things nobody else saw, were the ones who weren't satisfied with just knowing. They wanted to understand, really understand, down to the bones. Here's something I want you to think about. We live in a world now where information is everywhere. You can look up anything in seconds. You can watch lectures from the best teachers, read papers from the leading experts, access more knowledge than any library in history. And yet, I'm not sure we understand things better than we used to. Maybe it's because we've confused having access to information with understanding that information. They're not the same thing, not even close. I can look up how a radio works. I can read the explanation. I can nod along. But unless I've actually thought about it, really thought about it, worked through it in my own mind, I don't understand it. I just know what someone said about it. There's a world of difference between those two things. So here's what I'd suggest. If you want to really understand something, anything, not just physics, pick something you think you understand, something from your work, or your field, or just something you're curious about. Now try to explain it out loud, as if you're teaching someone who knows nothing about it. Use simple language, no jargon, no fancy terms, just clear, plain words. When you get stuck, and you will get stuck, that's where you don't actually understand. That's the gap. Don't ignore it. Don't paper over it with vague language. Sit with it. Think about it. Go back to basics. Work through it until you can explain it clearly. This is uncomfortable. It's much easier to stay in the comfortable illusion that we understand things because we can recognize the words. But if you can push through that discomfort, something wonderful happens. You start to see connections you never saw before. You start to ask questions that never occurred to you. You start to think for yourself rather than just repeating what others have thought. And that's when understanding becomes something more than just knowing facts. It becomes a way of seeing the world. I'm an old man now. I've spent my whole life thinking about how nature works. And the more I understand, the more I realize how much I don't understand. That might sound pessimistic, but it's not. It's actually thrilling. Because every real understanding opens up new questions. Every answer leads to deeper mysteries. That's what makes this worth doing. People sometimes ask me, what's the secret to being a good physicist or a good thinker? I don't think there is a secret, really. It's just this. Be honest about what you don't know. Be patient with confusion. Be willing to start from the beginning, no matter how simple that beginning seems. And never, ever fool yourself into thinking you understand something when all you've really done is memorize someone else's understanding. The world is stranger and more beautiful than any story we tell about it. Our job, if we're curious, if we care about truth, is to look at the world as it actually is, not as we wish it were or as we've been told it is. That's all understanding really is. Seeing clearly, thinking honestly, being willing to be wrong. And you know what? That's enough. That's more than enough. It's everything.